Hi everyone, my name is Rojesh, and in this video we are going to talk about the basic fundamentals of reinforcement learning. So reinforcement learning is type of machine learning. There are generally three types of machine learning that we generally talk about. The first one is called supervised learning. So in supervised learning, what we do is we have certain data x and y. X is features and y is a target that we want to predict, and we pass this data to certain um, algorithm which tries to figure out a certain function, which later can be used to pass new features x to predict the target values. In unsupervised learning, the second type of machine learning, we do not have this target, we only have this data x, and from this data we try to identify certain patterns. It can be clusters, it can be certain anomalies, or it can be certain association rules between different features themselves, or certain other algorithms. And thirdly, we have reinforcement learning. So what's reinforcement learning? Let's figure out. So in reinforcement learning, we have an agent that interacts with the environment. So agent can be anything. It can be a robot or a player in a system. And the system is our environment. This environment can be our board or our workspace the robot is working on. So let's take the example of TicTacToe. So TicTacToe, we have an agent. We have an environment state, which is our environment is a board of 3 by 3, right? And the agent performs, or the agent are the players who are playing this game. Agent performs certain actions on the environment, and it chooses certain actions from a namespace action space A. So the action an agent can perform in this environment is to place not or crosses in one of these 9 positions. So let's place our position here, and the agent immediately sees what is happening to the environment. It receives certain observations. It can get some observations from the environment, observation of the board, right? Oh, from the observation space. In our case, the agent can completely observe what is happening in the environment. In many other games, we might not be able to see what is completely happening, what is the overall state of the system. So in those cases, the observations might not be similar to the state. So this is the state of the environment. Yes, this belongs to overall state space of the environment, capital S. And the game continues. So a sequence of actions happen. So let's play a game here. The second one is the first player moves, second player plays a certain action, then the first player moves, plays another action, then again the second player takes certain action, and this continues till a player win, right? Player 1 wins. So what we can see here is that the agent and goes through a multiple number of steps: state 1, state 2, state 3, state 4, and state 5, before finally receiving a reward, right? Here the player 1 wins, so it receives a reward of, let's say, +1, while the player 2 receives a reward of -1 as it loses. In all other states, the reward is 0. In all other states, the reward is 0. Or equal to 0, or equal to 0, or equal to 0 for both of the players. So from this environment, it receives certain rewards. Alright. So you can see the reward the agent receives is at the end of the game. In many real situations, the reward received by the agent for the actions it has taken from the starting is at the end. So there is a concept of delayed reward, which is a delayed consequences of the action it has taken. As you can see, the game progressed to multiple states, and at each state, let's say at state 2, the agent only needs to know this current state to further predict or to choose an action for the next state. So the current state contains all the necessary information for the agent to predict the future. This type of process is called Markov decision process, or MDP. So it is characterized by a transition probability, probability of new state and reward given state and action. So for our case, given certain state and taking certain action, we will definitely reach certain state, new state, and certain receive certain action reward R. So it is deterministic, right? So this would be equal to 1 for our case. So it's certain. So our goal for this agent is to take certain actions based on a certain policy, right? And we call that policy by policy by alpha given state. So this is what is actually happening when we're talking about learning. So a reinforcement learning does this. It tries to learn a policy by which allows you to take actions for a state by interacting with the environment, that is interacting with the environment, which allow you to receive the maximum cumulative reward over time. So by learning, here we mean the agent learns a policy by of action given certain states, and this policy will allow it to maximize the total reward received over time. Okay, you can think of policy as a mapping between certain states to certain actions. So if it's deterministic, so for every state we have action that maximizes, that has the maximum policy or maximum reward, right? In like stochastic cases, a policy would return a probability of different actions with different probability, right? So this is type of stochastic policy. So the goal is to maximize the total reward. R1 in the first step, R2, R3, R4, R5, right? So these are total rewards that the agent received here in this case. But generally we are trying to, this is the reward actually received in this game, but in our goal, we are trying to maximize the long-term future rewards, the rewards which are not yet received, right? So the game has not yet completed or played. So what we do is we try to form some sort of expectation of the future rewards, right? The total reward is RT plus RT plus 1 plus RT plus 2 plus RT dot 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 T plus 3 plus dot dot dot, right? These are all the future rewards that the agent will receive. So however, all of these rewards are not equally valuable. Generally the immediate rewards are more important for the game, and far like rewards at the future is less valuable. In tic-tac-toe it is valuable because the future is the place where we are going to reach a reward, but in general cases the immediate rewards are much more valuable than the rewards at the far end. So in such case what we do is we use a discounting technique. So we calculate something called discounted total reward. So we discount the rewards of each time step. Gamma RT plus 1 so this equals to sum infinity gamma k RT k plus 1, right? So RT plus k. So these rewards are not yet obtained, so we take expectation of these rewards. So the expected total reward GT so this expectation is is called value function, and there are generally two type of value functions in reinforcement learning. One is state value function, that is expectation of GT given certain state, right? We call this V, and we take a value function for certain policy pi, and we have another value function called action value function, and we call it Q. We take it according to some policy, and it is the expectation of the total discounted reward for certain state and for certain action. So another name for action value function is also called Q value function. Okay, so now how do we relate this expectation to the rewards and the states and the actions that we take? So we have a state, and we take certain actions, and we come up to different types of there is a probability, like in our case it's deterministic, and we will always receive the same action, but there is certain probability in general cases to receive get into different states, S1, S2, S3. So we call that transition probability is right, and this is the probability, this is the probability, transition probability of transitioning to the new states, and each state has certain expected reward for the new state, right? Expected reward. This is the expected reward for the new states. So this total value is actually the total value reward that after taking reward for taking this action, right? We have an equation called Bellman's equation that relate this state action and rewards to the expectations. So what it says, it's like expected reward at the current state is equal to immediate reward plus uh, expected reward for the next state. So immediate reward is generally R, and this expected reward for next step is this kind of this value, right? And the derivation is actually long. We have to expand this expectation and do a lot of calculations, do a lot of processing. So what I'll do is just write the equation and explain the how that equation actually works. So the derivation for Bellman equation will give us the state value function as all the possible paths that the we can take at a state, sum of all transition probabilities to current reward and discounted future rewards, right? So you can, as you think of this as the immediate reward, the future reward for the next state discounted by gamma, and this is the transition probability, and this is the policy. And summing up all policy means like we are summing up all the actions that we can take on a particular states. Similarly, we have a Q value. Similar, all the transition probabilities plus R gamma, we will choose sum over all action next state and Q values of the future states. So transition probability, we have transition probability, and what we are doing here is we are taking the current reward and all the possible states our new state can take. The new state it is because like Q value is for taking states to a new action, and we come up to a new state, just as right. So we are taking all the possible actions in the new states and calculating all the possible Q values from that states, and we assume it as the expected rewards for the next state. So this is these are two our Bellman equations. So here what we want to do is we want to find the optimal policy pi, right, so that we have the get the maximum value out of this. So for all pi, what we have is like pi star is always greater than or equal to pi. It's the maximum pi that we can have for all pi, and what we come out of this is we have all the state values which is equals to the maximum state value. Similarly, the Q value for pi star is also the maximum Q value that we can have. So from this what we can say is that pi star, yes, is argmax a of our q value comma a given by the Bellman equation. Okay, now let's talk about this function again. So we have q value. We want to find out our q star, right? So we have a q value. Q star is actually the transition probability with r gamma right. And since in our case it's a tic-tac-toe, so it's deterministic, so we can assume it to be 0. So now we can use this equation to actually find the q values for our cases. So what we are doing, we can use one of the common algorithm that we use is called value iteration algorithm, and we use q value q learning algorithm, where we iterate over this q value. So the steps are very simple. So in like it's very common to other iterative algorithms. Like in any iterative algorithm, we initialize the q value, we choose certain actions based on the q value from q, and from this we perform certain actions, and we come to new states, and we also measure our new reward, and based on this reward we update our q value. So how do we update the q value? So update rule is also simple. We use the same algorithm. So generally what we do is we have an existing q value, right? So we have an existing q value and we want to update with this our new q value. Let's say we call it q new. So we choose certain kind of certain learning rate, right? Certain learning rate, let's say alpha, and we try to choose a range between old new and new q value, and we update it to the q value, right? This becomes our q update rule becomes q plus alpha q star minus q, right? So the algorithm that we are using in our code is also similar. It's q plus equal to alpha gamma, in our case we are just using gamma reward minus old q. Okay, so this is, so another thing that we have to also look into this is the idea of exploration, the trade-off of exploration and exploitation. See here, when we are doing this q learning algorithm, so we have, when we start with initializing the q value, and then we chose certain q value from the initial q, we chose certain actions from the initial q value. So this part is exploitation. So we are already exploiting the knowledge we have, and another value is another action we are doing is updating the q value. We perform certain action based on the q value and update a new q value, right? This is a kind of updating a new q value or finding a new q value, right? And coming up with a new q value is the idea of exploitation. So exploitation, finding new q value and exploiting existing q value, and we generally choose certain trade-off between how much of split of exploitation and exploration we want. We have marked it as epsilon in the code. So that's it for the overall fundamentals of reinforcement learning. I hope it was helpful. Thank you.